who uses a computer for just one thing anymore? We all have way too many tabs open on our browsers. We always have some other window up in the background to distract us. We all multitask. It would be almost laughable if someone tried to sell us a computer that could only do one thing at a time. That's just not enough throughput. We've become accustomed to much more. Multitasking is one of those features that I think offers up a really interesting story. It's a feature that makes good sense. It's something people really want, and it turns out we really like it. It also makes us more productive. At least, in theory, it's supposed to make us more productive. So, it should be no surprise that once we figured out how to make a computer run more than one program at a time, well, that kind of became the golden standard. This was initially called time sharing, and while it's always been a pretty complicated feature, it became near ubiquitous on larger computers. But this did take some doing. Time sharing requires a certain level of sophistication. Not every computer is suited to it. Interestingly enough, time sharing was theorized well before it was ever put into practice. Papers discussing the possibility appeared in the mid-50s. Implementations don't appear until the next decade, and even then it's all small scale to start with. But once things get going, there was really no turning back. Well, mostly there was no turning back. By the 1970s, time sharing was the norm on computers, but the definition of computers was about to change. Intel announced the 4004, the first commercial microprocessor. Competitors followed. Suddenly there was a new type of computer, the microcomputer. It should be pretty clear that microcomputers, the machines we all use nowadays, can in fact multitask. The thing is, it took a little while to get there. The process mirrored the development of time sharing, from theory to early steps to ubiquity. And just like time sharing, the early steps, while somewhat obscure, are perhaps the most interesting. Welcome back to Advent of Computing. I'm your host, Sean Hass, and this is episode 82, Juggling Jobs with OS-9. Today, we aren't talking about Apple's OS-9, but instead an operating system developed in the late 70s by a smaller company called Microware. That operating system was also called OS-9, stylized with a dash just before the number. What exactly is OS-9, you may ask? Well, dear listener, I'd like to present this small operating system as a fascinating stepping stone. Call it an ideological missing link if you want to be a little overly dramatic. OS-9 was an operating system developed initially for the Motorola 6809, an 8-bit microprocessor. It's a neat little chip that would see some use in the early era of home computing. Like its contemporary silicon wafers, the 6809 was small, relatively cheap, and relatively weak. That was just what microprocessors were in that era. Then along came OS-9. This system offered one big feature that home computers just lacked: time sharing, or, if you prefer, multitasking. OS-9 could not only run multiple programs simultaneously, it could also allow multiple users to share a single computer. The software features of this operating system were more in line with big iron offerings, but it was running on a piddly little home system. The computers OS-9 targeted would have memory measured in kilobytes, maybe tens of kilobytes if you were lucky, but it could juggle multiple processes and multiple users at once. On the surface, that should sound at least a little impressive. It honestly is. Diving into the details, well, that makes OS-9 even more exciting. Most larger computers, mini computers and mainframes, had specialized hardware to facilitate time sharing. There were a number of reasons for this. The bottom line is that improved hardware tends to make time sharing easier to manage. This era of microprocessors didn't have equivalent hardware, at least that equivalent hardware wasn't widespread. As a consumer, you were happy to be able to loop, and multitasking wasn't really on your radar, not really. The earliest versions of OS-9, called Level 1, explicitly targeted computers without any of the special time-sharing helping hardware. Now, as with everything, there is a larger context here. What is OS9 a stepping stone towards? Let's call it the home computer's coming of age. Early microprocessors, the first generation that started being produced in the early 70s, they couldn't really do much. The 4004, for instance, was just barely more powerful than a calculator. Really, perhaps better put, it was more flexible than a desktop calculator. The next generation, chips like the 8080 and the MOS 6502, were a bit more powerful. However, they were still limited. These chips could function like computers, but they were missing, a bit of the oomph of larger machines. Once a new slate of chips hit the scene at the end of the 70s, we start seeing more advanced features. OS9 was one of the early operating systems to really take advantage of those features. The sum total here is that as the 70s move into the 80s, we're seeing home computers pushing more and more to emulate their larger cousins. Sure, an Altair 8800 is great and all, but wouldn't you rather have a PDP tucked under your desk? This episode is going to be one of those Comp Sci 101 kind of affairs. To really understand why OS9 is so rad and why the march towards mainframeification is such a big deal, we need to cover basics. Our discussion will start by looking at the special hardware that made time sharing possible, or at least facilitated it. From there, we're going to jump forward a little bit and start looking at Motorola's new chip, and then finally OS9 itself. Welcome to class. Since we're all fancy academics here, I figured it would be best to start off with a clipping from a very fancy and very academic-sounding paper. So, if you'll allow me, quote, "The speed at which digital computers operate depends heavily upon how fast the processor can get data and instructions from memory. Over the past quarter century, the internal organization of computers has become increasingly sophisticated as a result of efforts to make data more readily accessible to the central processing unit. In parallel with this engineering activity, systems programmers, installation managers, and computer scientists have been striving towards the same goal. Their effort to optimize the processor's access to information has come to be called memory management." End quote. That's from a 1981 ditty titled The IBM History of Memory Management. Once again, you've fallen for my trap. You've thought this was an episode about time sharing or multitasking, maybe something about computer history. But you're wrong. This is another lecture about how cool memory is. A lot of this episode is going to actually be concerned with how memory is used and how it became better utilized, so be prepared. This IBM paper is talking about the fact that, over time, we've had to find better ways to deal with memory. A machine like ENIAC didn't really have addressable memory at all. The same goes for earlier analog machines. The earliest problems people wanted to solve were simple mathematical calculations. That doesn't always require a lot of memory, and in a lot of cases, it actually doesn't require any real memory at all. But that changes as problems become more sophisticated, as computers can handle larger tasks. Really, once computers are created, we can start solving different problems. We can start asking questions that you can't do with normal math. Now, it's tempting to break this up into eras, maybe call the early period the era of processor primacy, and then we move into the era of memory primacy. But hey, I think that's kind of dumb. The first stored program computer, EDSAC, was based on designs that were drafted while ENIAC was still under construction. The so-called era of processor primacy may have lasted for months, if we really want to be generous there. Stored program computers are really where it's at. So that's the memory model that we're going to start with today. In the most basic setup, you have a processor, the part that does the crunching, and some type of addressable data store. These are connected by two buses, the data bus and the address bus. The data bus is just what's used to move numbers back and forth. It's not super interesting for our purposes today. The address bus is where a lot of innovation is hidden. This bus is used to specify the address you want to access. That may seem simple, but it actually leads to all sorts of interesting and frustrating problems. A prime issue is the most simple one. How wide is the bus? When talking about the size of digital data, it's traditional to call it width. I've tried figuring out why we call it that, and I have yet to see a definitive answer. So here's how I think about it. Each bit on a bus requires a physical connection, whether that be a wire, a trace, or maybe a thin region of doped silicon. A bit is just an on-off value, thus it has to have some physical pathway to travel. When you need to move more than one bit, you bundle those connections up into a bus. Most often, these buses are laid out with their wires side by side, so you have what looks like a big, wide ribbon. The width, then, can easily be understood as how many wires actually make up this wider bus, the width of this physical ribbon. Memory access requires you to use the bus. In the most simple case, the processor will just put a value on the address line to specify the location in memory it wants. A pulse is sent out on a separate line to tell the memory device that someone wants to read from it. Then the memory device will grab the data stored at the location specified on the address bus and send that value back to the processor over the data bus. It's important to note that addresses aren't anything special. They're just numbers that have to be expressed in binary like any other number on a computer. That means that they have all the usual restrictions. These are whole numbers. I think that should go without saying. You can't have address 1.5. They also exist in a range dictated by the size of the bus. So if your processor has an 8-bit wide bus, then your highest memory address is 255. I know, I often talk about how digital computers are great because they have managed to overcome older physical limitations. Well, this is one case where those limitations do like to stick around. The point here is that when it comes to the address bus, size matters a lot. A further consideration, and a bit of a tangent, is how the processor internally represents data. This becomes relevant when dealing with pointers, that is, variable values that reference some address in memory. You usually access a pointer by first loading the desired address into one of the processor's registers. Then you tell the processor to take that register, treat it as an address, and you're good to go. The easiest way to account for this addressing by register is just to have each register that can be used as an address pegged to the same width as your address bus. If your bus is 8 bits wide, then so are all your addressable registers. But that's not always the case. On occasion, a processor's registers will be a different size than its address bus. You can end up with a computer that uses a 22-bit address bus, but only has 16-bit wide registers. There are ways to deal with this, which we'll get to in a second. So far, this has all been addressing the most simple possible case, where you have a direct connection from your processor to your memory. Each line of the address bus on the processor matches up to a line of the address bus on the memory device. Simple, direct, easy. But life isn't simple, and computers are rarely easy. Let me paint a picture for you. Let's say you have a fancy new research computer. The processor is complete, it works great, and all wired up to the rest of the system. You have a shiny new 24-bit address bus, wide enough for any future needs. However, you don't have enough RAM. You wanted to use new magnetic core memory, the fast RAM that's sweeping labs the world over. But your grant funding can only cover 16 kilobytes of core memory. Your bus is wide enough to fit megabytes of RAM, but that's just too much for your pocketbook. A similar situation played out at the University of Manchester in the waning years of the 1950s. The university, in collaboration with Ferranti and Plessy Corps, were designing a computer named Atlas. This is a story I'll dive into in more detail on another episode, but it makes for a really good setup here, so I can't resist. Atlas was targeted to be a commercial system, at least on a small scale. At the time, magnetic core memory was just the best option for short-term data storage. It was fast, reliable, and 100% random access. But it wasn't very cheap. A fun little fact is that the production of magnetic core memory was almost impossible to automate. This kind of memory was built from tiny ferrite washers woven into a mesh of copper wire. So, for many years, it had to literally be woven by human hands. That kind of labor doesn't come cheap. Atlas was designed to use 16 kilobytes of core, not really enough to get much done. This was augmented with an additional 96 kilobytes of magnetic drum memory spread across 4 separate drums. Now, magnetic drum memory is a bit of a strange beast. It works by spinning a magnetizable drum under a set of pickups. If you want all the fine details, then you should check out my recent episode on magnetic core and why it's just so much better. The summary is that drum-based memory was slow, not as reliable, and had to be accessed somewhat sequentially. There were at least restrictions. But it was cheap. So the question becomes, how do you make a single computer that uses multiple types of memory? Drum and core memory each have their own specific characteristics. They each have to be used in a specific way. As I will remind you from IBM's History of Memory Management, quote, over the past quarter century, the internal organization of computers has become increasingly sophisticated. To make this all work, Atlas had to become a more complicated kind of computer. It couldn't just have the processor wired directly into its memory. Atlas needed something to sit between the two and deal with all this nasty stuff. The solution was called the One-Level Store by Atlas's designers. We know it today as virtual memory. In the most basic sense, virtual memory is an abstraction on top of physical memory. So far, we've been discussing the physical level, the actual wires and ferrite beads that make up memory and its associated buses. While that's an important level, it's a bad place to be if you're a programmer or, by some strange twist of fate, if you find yourself as a program. You really just want to say, hey, give me some memory, and let some deeper machinations take care of the specifics. Atlas implemented these deeper machinations using a combination of hardware and software. The actual implementation is relatively simple. Here I'm pulling from a 1962 paper on Atlas called, fittingly enough, One-Level Storage System. The trick here had to do with shuffling around resources. Memory on Atlas was broken up into 5 12-word chunks called pages. During normal operation, a program could request data from any given page. So you had access to the full address range. But there was an intermediate layer between you and the physical memory. In the most simple terms, we could say that Atlas used its faster core memory as a cache to speed up performance of its slower drum memory, but it's a little bit more complex than that. Each page in core had an associated PAR, or page address register. These were just entries in a table that listed which page of drum memory was stored in which page of core memory. When a user tried to access a physical memory location, Atlas first checked the PAR to see if the requested location was loaded into core. If so, then Atlas redirected the program to the proper address in core. So you might ask Atlas to return a value at address OX100, but actually be served the value at address OX005. That first number, the address you asked for, is often called the logical address, while the actual location of the data is called the physical address. The shuffle occurs if you try to access data from a page that's not loaded into core. In that case, Atlas fires off a routine to grab that page off the drum, find a free PAR, and then load the page into core memory. There's some record-keeping kind of stuff that goes on in the background, but that's the basic rundown. In Atlas, for the first time, we see a processor that isn't wired directly into memory. There's this intermediary agent. So why does this virtual memory or one-level store, or whatever you want to call it, matter for time sharing? Well, to put it simply, it lets you pull some sick tricks. Here I've been highlighting virtual memory because it was the earliest tool in play. It helped Atlas reduce overall costs, but it was just as easily applied elsewhere. You see, you aren't limited to switching between two different types of memory. You can use any kind of storage as long as it can hold data and is at least reasonably fast to access. As hard drives entered the fray, mainframes started using them as secondary storage for virtual memory systems. With this tweak to the technique, you could now have a computer with theoretically limitless memory. I mean, there are limits, but it was one way to break past the address bus barrier. If you needed more memory but didn't have any space left on the bus, all you had to do was swap. Just take a chunk of RAM that's not being used, throw it on disk, and presto, you've just made more RAM for free. On its own, virtual memory is fancy. I mean, who doesn't love the ability to just lie your way into having more memory? That's pretty sweet. When used in conjunction with time sharing, things get really slick. If you set up everything right, then virtual memory and paging allow two programs to operate on the same computer in total isolation. This is all possible thanks to the split between logical and physical addresses. It's usually accomplished on the operating system level with a little help from specialized hardware. Since logical and physical addresses don't have to line up, a program can request one address, but the operating system can decide where to route that request. Just tie that routing into the process and you're good to go. Each process can have its own set of pages that don't overlap with any other process. Thus, two programs could read from the same address at the same time, and thanks to the wonder of logical addresses, they could be given different values. This is really safety at its finest. To the program, it seems like it's all alone, but in reality, it could be running on a very crowded machine. But it can never be exactly that easy. Introducing this extra layer between memory access and physical memory introduces a new issue: performance. Any added operation here eats into CPU cycles. You'll never be able to get back to that baseline speed of one access equaling one operation. The worst case scenario is that you have to do all of this purely in software. You have to write some custom code that intercepts every time a program tries to access or really do anything with memory, and then does this shuffle translate boogie. But luckily, we can do better. One solution, and the one I'm most familiar with, is the so-called paging box developed at MIT for use with the Incompatible Time Sharing System, or ITS. This was, quite literally, a physical box that sat between the lab's PDP-10's processor and their memory. A bus allowed a program on the PDP-10 to configure how data would be paged, basically a fancier descendant of the PAR tables used in Atlas. Then the box would handle the rest. This has the advantage of freeing up the processor. In theory, at least, this could bring these mediated memory operations closer to raw access performance. The paging box had one other ability. It implemented memory protection. This is that time-sharing trick I mentioned, just in physical form. The paging table included options for restricting access to specific pages. So when setting up a table, ITS was able to instruct the paging box to keep certain chunks of memory isolated from other programs. Thus, time sharing was not only made easier to implement, it was also made more performant. This whole realm of physical devices that sit outside the CPU and handle memory operations are called Memory Management Units, or MMUs. They're really nice, especially for time sharing, and they've become standard on computers. But back in the day, when home computers were just starting out, MMUs were mainly a big iron thing. I mean, why would you need all that power down in wafer world? There's always been a certain drive to create microprocessors more in the mold of large computers. We could look at this in a number of ways. Mainframes and minis are just more capable machines. There's no better way to put that. You can do a lot more in a big system thanks to all the features available and thanks to their larger size. More memory means more code and data. Faster processors means you can save time crunching numbers. For Motorola, these features also meant costs could be cut. In the 70s, Motorola got in on the processor game. If you want a larger roundup, then go check out my episode on the 6502. The whole first half is all about Motorola. Anyway, the Big M's first offering was the 6800. Part of the 6800 team split from Motorola and they went over to another company called MOS Technology. There, they built the 6502. This second chip is essentially a cost-reduced and feature-reduced version of the 6800, designed thanks to client complaints. Perhaps unsurprisingly, the 6502 would become the more popular of the two processors. At this point, Motorola, as well as the defectors over at MOS, were targeting the embedded systems market. That is, the 6800 and 6502 were planned as ways to give machines a little bit of smarts. Motorola's initial vision was that the 6800 could be one of a number of building blocks, prefabricated chips that could be thrown together to quickly build an embedded computer. Why go with this approach? Well, once again, it all came down to cost cutting. I'll cut you in on a little bit of career advice. It's something of a secret, so don't go sharing it. Software costs are almost always higher than the cost of hardware. Just think about it. For every computer, you end up using multiple different programs. Each of those programs had to be written by human hands. We usually count the amount of effort spent developing software in human hours, and some programs are easily in the human year range. Humans tend to be paid by the hour, and since software development takes a lot of time, that means that software isn't cheap to develop. As I've said before, high-level programming languages were invented to make programming faster. Even with those tools, programming good software still takes huge amounts of time. So software is always a pretty secure field to work in. Motorola was attempting to offset their clients' software development costs by providing a box of relatively standardized and reusable parts. The idea here was that if, say, you wrote an interface program that used one of Motorola's compatible I/O chips, then that program could be reused on later projects that used the same chips. It's all in the same family, but here's the thing. The 6800 was a pretty primitive chip. I haven't programmed for the 6800 before, but I have spent some time dabbling with 6502 assembly. These processors just don't have a whole lot of support for fancy software. By that, I mean you end up writing out a lot of assembly by hand without shortcuts. For instance, neither the 6502 nor the 6800 have a multiply instruction. That's left as an exercise to the programmer. That's annoying, but there's something worse. When programming the 6502, my biggest hangup was the chip's lacking register set. Both these 6XXX chips are 8-bit, meaning that internally they like to operate on 8-bit numbers, and they use an 8-bit data bus externally. However, they also sport a 16-bit address bus. This leads to some, well, awkwardness, to put it lightly. The 6502 deals with this mismatch by providing two 8-bit registers, X and Y. They can be combined to describe a full 16-bit address. The 6800 provides a single special 16-bit index register that serves the same purpose. Either way, these chips have to be specially designed to take advantage of their larger address bus. That leads to a fun issue. How do you write a program for these chips that compares two strings? Let's assume that each string is held in memory at some address. You have to have some way to tell the program where these two strings are. But you can't use registers for that since, well, you only have one register that can hold a full address. There are a number of ways around this. One is to use a stack for passing arguments, but these chips don't really have very sophisticated stack support. Luckily, we have an out. The 6800's designers knew this kind of problem would arise, so they gave us a special direct addressing mode. Now, addressing modes in general can get a little confusing, and the name sounds a little more grandiose than it actually is. A computer usually has multiple ways to talk about memory. The most simple is explicit or constant addressing, where you give a literal address as a number. You can also address by the value in a register, often called indirect addressing. The direct addressing mode of the 6800 is a little different. It takes an 8-bit address either as a constant or from a register, then assumes that the upper 8 bits of that address are 0. In practice, no one really calls this the direct addressing mode. They call it the 0 page, since, it only works for direct access to the lowest chunk of memory. 0. The 6800 as well as the 6502 implement this feature. 0-page access is also a little faster than other memory modes. And in programming practice, the 0 page is often used for passing parameters to functions and holding temporary values. So that string compare function that I mentioned, well, you can just put both addresses somewhere in the 0 page. Easy peasy. But, dear listener, life can never be that easy nor peasy. Aggressive use of the 0 page leads to a very specific problem. It can create unsafe code. Now, the setup for this is a bit complicated, so you're going to have to bear with me for a minute as I paint a word picture. To get to why the 0 page can sometimes lead to problems, we need to talk about interrupts. Interrupts offer a fun little wrinkle to normal computer operation. An interrupt is a mechanism by which normal execution can be, interrupted. When an interrupt fires, the processor stops, stores its current state, and then starts running what's called an interrupt handling routine. Once the routine is done, the processor grabs its saved state and then restarts from where it was prior to being interrupted. This mechanism is most often used for input and output devices. When you hit a key on a keyboard, that tells a controller to fire off an interrupt. The processor then stops what it's doing, runs a keyboard handler, and then gets back on task. It's a really nice mechanism that helps us write better code. Instead of having some main loop that's always running and checking for keyboard inputs, we just need an interrupt handler. The keyboard handling code is only executed right when it's needed, so we save a lot of processor time. However, not all chips are equally well suited to interrupt handling. Here we get back to the 6800 and 6502 and to the dangerous 0 page. Let's say you have a keyboard interrupt handler set up, and your code is currently running that fancy string compare that I keep talking about. You've decided to use locations 002 and 004 in the 0 page as arguments to your string compare function. Then, someone presses a key. Your currently running program is put off to the side for a minute, and the processor starts dealing with the key press. What would happen if the keyboard handler also used address 002 in the 0 page? What if that was where it stored the value of that key press? The result would quite obviously be disaster, or at least your nice program would get a little trashed. So to make everything play nice, you have to have some pretty fine-grained control over your code. You have to make sure that any interrupt handlers aren't clobbering any locations in the 0 page. An interrupt can happen at any time, so you have to always write around that possibility. In legal terms, you could say that interrupts have, at least on these chips, a chilling effect. They impose limits on how you can program, and what resources you can use in that program. This gets a lot more dangerous if you're using an interrupt handler that you didn't write. How do you handle that level of coordination? What if the code, unbeknownst to you, is using the same chunk of 0 page that you need for the rest of your program? For the keyboard example, this might be a little annoying, but we can do worse. Preemptive multitasking is the most common kind of multitasking nowadays. It was also the trick that originally facilitated time sharing. In this model, programs are preempted, as in the operating system switches to a new program at some interval of time. The current process gets stopped, no matter what it's doing, and another process starts execution. This is commonly handled using a programmable interrupt timer, a circuit that repeatedly fires interrupts at some predetermined time. Preemptive multitasking functions something like this. The interrupt timer fires off an interrupt. The processor stops what it's doing to handle that interruption. From there, the current program is suspended and a new program is chosen. The chosen program is then unsuspended and resumes execution. This continues until eventually the suspended program is back in the foreground, and then the loop just keeps cycling. To this initial program, the one that gets suspended, it looks like an interrupt just fired and then returned. It may have been suspended for milliseconds, or it might as well have been suspended for days. It can't really tell, and crucially, it could have been suspended in the middle of some delicate operation. Now think about this in the context of the tiny 6800 and 6502. Think of it in the context of the 0 page. Maybe the first process was setting up a string compare. It just put a few addresses into the 0 page. Then, before it actually called that function, it was preempted. Another process starts running. This second process also does a string compare. Hey, it's a popular function. When the first process resumes, it finishes up making its own string compare call. The addresses that it just set up in the 0 page have been changed. Suddenly, it's comparing entirely different strings, and so all your careful planning has just fallen to pieces. That's what happens without some type of memory protection. This is exactly why memory protection is so important. It stops a dangerous form of cross-pollination in your address space. That's also why many early microprocessors were poorly suited to multitasking. The 6800 and 6502 are a fun example because they lack any kind of memory management unit, and the 0 page promotes a dangerous type of programming. At least, it's dangerous in this very specific case. This was one issue facing Motorola as the MOS 6502 started to outsell their own 6800. Motorola needed to make a new chip to try and reclaim some market share. One solution was to take the successful part of the 6800, the hardware building block approach, and expand that into the software domain. Their new chip, dubbed the 6809, would be designed to better support complicated software while retaining some compatibility with the 6800. A big part of this facelift was low-level support for multitasking. At least, that was the core idea. So on to the brass tacks. How did the 6809 actually help with multitasking? It's more accurate to say that it didn't really support it, but it gave programmers tools that made multitasking easier to implement. The first tool in this utility belt was the ability to change the 0 page. In early 1979, Byte ran a series of articles discussing the development of this new chip. It outlined the rationale behind the development of the new toolkit. The chip had a very software-centric approach that I haven't seen all that often. It's kind of refreshing. During the early stages of development, Motorola actually surveyed existing 6800 software to see what programmers were actually doing with their hardware. I can't stress this enough, that's just a darn good idea. Motorola also took a page from the 6502 defectors and gathered client feedback. The 6809 would be molded by these two big inputs: analysis of existing code and complaints from existing programmers. The first tool to be slotted into this new utility belt was comprised of changes to the 0 page. I think I've made a good case that the 0 page, while being interesting and useful, was a little bit unsuited for truly complex software. The 6809 replaced this inflexible storage with something better. From the Byte article, quote, "The direct page register can also be used effectively and safely in a multitasking environment, where the real-time operating system allocates a different base page for each task." End quote. This I think, is an interesting step towards small memory management hardware. The 0 page, called the base page here, was replaced with a movable chunk of memory. The direct page register was used to specify where the base page would be located. Access to the base page would be accomplished the same way. A program would just ask for a location between 0 and 255. But the upper 8 bits of that address would be pulled from the direct page register. A direct read of 001 could be pulled from 001, or it could be pulled from something like 123001. The 6809 translated from a logical address to a physical address using a configurable value. It's less flexible than something like the paging box used by ITS, but it has a similar flavor. It's a similar solution. This also introduces an interesting possibility. In 1976, Texas Instruments debuted their TMS 9900 processor. This chip had a somewhat similar mechanism of action. It used a chunk of memory for its general-purpose registers, so when you interacted with a register, you were really interacting with some location in memory. Where those registers were stored could be changed on the fly. This was also useful for multitasking. In turn, this design stemmed from earlier TI computers. The side point here is that the idea of a chip mimicking a larger machine didn't start with Motorola. This was an older lineage. So, is there a connection here? I'm not entirely sure. The 6809 was primarily designed by two people, Terry Ritter and Joel Bonney. I haven't seen any connection between these two and Texas anything prior to their work at Motorola. That doesn't preclude the possibility, but it takes away a smoking gun. I'm bringing this up to point out that the idea of moving around some special block in memory isn't unique to Motorola's new chip. It was a technique that was already out there. Anyway, the revamped 0 page, or the base page now, was the first big step towards multitasking. This is also the big flashy part. Interrupts could now use a special 0 page. Each process could, in theory, have its own 0 page. The method of action here meant that a program wouldn't have to have some hard-set direct page register that could be configured when the program was loaded. The other crucial tool that I need to address is a lot less flashy, and it's not exactly a single new feature. The 6809 had improved support for relative addressing. This is another type of addressing mode. The 6800 already had some support for relative addressing, but the newer chip expanded that support. Relative addressing just means that instead of giving some absolute address to a location in memory, you can just give a relative distance. So instead of saying jump to location 01534, you could just tell the processor to jump forward by 5 bytes. At first, that may sound a little underwhelming. I told you it's not as flashy. But relative addressing has one huge advantage. If you only use relative addressing, then you can create position-independent code. In other words, your program can be loaded into any location in memory. For small machines, this doesn't super matter, but it's crucial for time sharing. A program won't always be loaded into the same exact address, so code has to be position independent. The revamped moving 0 page plus improved relative addressing made the 6809 a great host for this kind of software. So, what about that software? What was actually running on this thing? This finally brings us to the long-promised topic, OS-9. The history of OS-9 is a little, well, undocumented. This is one of those stories that we have to piece together from manuals and magazine clippings. It all goes back to a company called Microware. The company was founded in 1977. As far as I can tell, their first product connected to Motorola was even more obscure. It was called RT68. We've already hit a side note that I need to address. The RT here stands for real time. As a 1978 article on RT68 in Kilobaud puts it, quote, adding the real-time portion means that the executive can alter its work in response to changing conditions in the real world. End quote. Executive here is just a reference to the fact that RT68 is an operating system-like environment. What bugs me here is this. The meaning of real-time isn't the same as the more modern use of the term. More recently, real-time operating systems have been described as systems that perform procedures within strict or guaranteed timing. A real-time operating system might, say, always respond to signals on the serial line within 3 milliseconds. Nothing I've read about RT68 implies that it had any timing guarantees. When Microware calls it real-time, they mean that you can type into it and get feedback in, real time. But hey, that's not what was going to be impressive about the offering. RT68 ran on the 6800, and it supported multitasking. The trade-off was that RT68 was a pretty bare-bones operating system, and all its multitasking was handled in software. We get some hints at how this worked in the 78 kilobaud article. It goes into pretty fine-grained detail on how multitasking was actually accomplished on the limited Motorola chip. RT68 kept a table of processes in memory. The table actually allowed for some pretty neat controls. Each task had a priority level. You could also set how long it could run before a swap occurred. This table also hides the slick trick in it, so to speak. Each entry had an address for the process's stack. RT68 set up a separate stack for each process. That is, each process had its own push-down stack that could be used for state data and function arguments. Once again, the 0 page was just too dangerous to use in a multitasking environment, so Microware had to provide some software-defined replacement. Anyway, I think if anything, RT68 gave Microware a good introduction to pushing small chips to their limit. You shouldn't really be able to multitask on a 6800, at least not in a very meaningful or nice way. But here we have Microware accomplishing just that feat. As we know, the 6800 wouldn't be long for the world. Soon the replacement chip, the sporty new 6809, came in to steal the spotlight. With the new chip came the need for new software, hopefully software that could show off the better side of the 6809. Motorola, as a hardware house, reached out to existing software vendors to have some code thrown together. Microware was one such vendor. As explained in the OS-9 System Programmer's Manual, quote, OS-9 Level 1 is one of the products of the Basic O9 Advanced 6809 programming language development effort undertaken by Microware and Motorola from 1978 to 1980. During the course of the project, it became evident that a fairly sophisticated operating system would be required to support Basic O9 and similar high-performance 6809 software. End quote. The logic here, at least in my twisty head, is easy to follow. Basic O9 was a pretty fancy dialect of BASIC. The package included a compiler as well as a more standard environment. Just as an aside, Basic O9 was advertised as being so well structured that you didn't need line numbers, so it's kind of a neat little dialect to see popping up. To support a big fancy language, you end up needing a lot of smaller components. For a compiler, you need some way to handle files, since you have to pass in source code and then store compiled binaries somehow. You also need some way to manage memory. Every time your code calls out to create a new list, for instance, you have to find somewhere free in memory to place that list. You also need some kind of user interface, since, a human is expected to use the thing. At some point in the Basic O9 project, Microware realized it would make a lot more sense to just create an entire operating system to support Basic O9 and any later projects for the 6809. Why reinvent the wheel when you can do it right the first time? Now, jokes aside, this was probably the right way to go. An operating system, once you shed all the artifice and whistles, is really just a toolkit for allocating resources and providing some kind of useful programming interface. Many of the resource management problems you need to solve when running a compiler or a programming environment, like BASIC, for instance, are already solved by an operating system. You could write up a bunch of libraries to reuse later, or you could go one step further and just make a full OS. We don't have very good information on the actual development cycle of OS9 beyond the whole basic to OS pipeline. So instead of more speculation, I'm jumping us right into OS9 itself. Hey, this is a pretty technical episode, so we're going to be sticking to that feel. The best resource I found is the aforementioned System Programmer's Manual. I think it makes for some riveting reading. A good observation to start with is that OS9 compares itself favorably to Unix. Microware's own literature talks about their small operating system in terms of a larger time-sharing system. I mean, right there, we're on the trail of how Big Iron was getting scaled down. Maybe call it small aluminum. So what exactly was being cut out to reduce the overall scale? You can't have Unix on a micro, at least not quite yet. So what did early 6809 adopters get? The main connections here are that OS9 offered full preemptive multitasking, just like Unix. It supported multiple users, just like Unix. It supported a hierarchical file system, just like Unix. And OS9 also exposed devices as files, just like classic Unix. That last point may sound like the most mundane, but I'd argue it's the coolest. You'll often hear that in Unix land, everything is a file. When I was first entering the Nix fold, I know I kept hearing that, and it actually took me a little bit too long to fully grasp the meaning. To put this a less catchy way, both Unix and OS9 offer a unified device interface. You don't have special functions for reading from the serial port, writing a file, and printing text. Those are all handled the same way. The common denomination that Unix went with was the file. To talk to a terminal, you just access a special file, something like dev.tty. That uses the same functions as reading and writing any other file. That makes programming for Unix really nice. It also means you can redirect data around freely. You can throw the outputs of a program into a file or out to the printer or anywhere you want. OS9 follows that same prescription. It's a pretty neat trick, but it's also a wonderful way to handle hardware. OS9 goes about this unification in, once again, a smart way. Can you tell I'm a little bit impressed by the design here? Anyway, this brings us to what OS9 calls memory modules. Just like the whole real-time versus real-time thing, there's a little bit of confusing phrasing here. To be fair, OS9 would eventually become a real-time system in the modern sense, but not for a while. Anyway, in OS9, a memory module isn't a physical module of memory. It's a loadable chunk of code wrapped with some information about that code. Basically, it's a specialized executable format. I'm not going to get into great detail about the code metadata, but there are two fields that we need to touch on. First, each module had a name. I know, groundbreaking stuff. Second, each module specified how much space in memory it needed for storing data. You see, in OS9, code and data are kept separate for a really slick reason. A memory module is different than a process. This is some subtle and pretty highbrow stuff. The best way to make sense is to go through how OS9 fires off a new process. Let's say you're starting up a text editor, call it edit. All you do is type edit at the command line and hit enter. OS9 then searches its table of loaded memory modules for a module named edit. If it can't find one, then it goes to search some paths on disk. Once found, the module is loaded. So far, all normal stuff. Once the module is found and settled in memory, OS9 allocates some space for the module's data. If edit says it needs 10 kilobytes, then OS9 goes and finds 10 kilobytes of memory for it. The first chunk of that memory is set up as a direct page, so the running process has its own isolated zero-page equivalent. The memory module and this data chunk could be anywhere in memory. They could be right next to each other, or they could be separated by kilobytes. Then OS9 passes execution to edit's memory module. To the user, it just looks like the text editor has finally loaded. So what happens if a second user tries to run edit? Or if, for some Weird reason, the initial user wants to run a second version of edit. OS9 finds the module in memory, then allocates some new space for this new data. Then it passes off execution to the module. Each instance of edit is using the same module, the same chunk of code, but they have separate chunks of memory for data storage. Each process has its own direct page for passing around arguments. All is isolated and safe, just as it should be. I think this is a really cool way to adapt multitasking to a smaller world. Normally, in a system like Unix, an invocation, that is, a call to load a program, does just that. It loads a program. That's fine, but it can waste memory. On a mini computer, you might have memory to burn, but OS9 was targeting machines that had something like 40 kilobytes of memory. To run at that size, you have to keep things lean, so it's better to reuse what you already have loaded. Microcomputers also didn't have fantastic storage options yet. The penumbra here was small, so to speak. You might have some tape storage, maybe a floppy drive or two if you were lucky. Neither of those devices are actually very fast, so once again, it's better to reuse what you've already loaded. To accomplish this thrifty feat, OS9 software had to follow some guidelines. The first was that memory modules had to provide information about what they were and how much space they needed. The code also had to be kept separate from its variable space. You can't have variables tucked away in reusable code. And finally, all your code had to be position independent. That is, you could only use relative addressing. The 6809 provided all the features needed to make that easy. And just remember, with the direct page, that relative addressing could be used in the same way as the old zero page. That definitely made things easier to adapt to. The upside here is that if we say that Unix could guzzle RAM, then OS9 practically sipped on it. This is a kind of efficiency born of necessity. The other upshot is that OS9 could do some really cool stuff. The core of OS9, called the kernel, was relatively small. All it had to do was provide a way to allocate memory, manage tasks, and some mechanism for handling memory modules. Sure, those are complex tasks, but that's not a whole lot of tasks. We have a short list here. Device drivers were also loaded as modules, just a special case of the memory modules used for normal software. And this was done dynamically at runtime. So, in theory, let's say sometime after you boot up, you decide you need to plug in a hard drive to the parallel port. You could just tell OS9 that it was time to load up the appropriate driver and you're done. No need to reboot, no need to recompile the operating system. You just load a new module. You could even write your own drivers for the device with relative ease. You could develop, debug, and build that driver inside OS9 itself while it was running. For home computers of the era, that was a whole lot of power. This was close to something you'd do on a mainframe. So hey, maybe the restriction here bred something really useful. In the current day, multitasking at home is normal. I don't think anyone would buy a new computer that could only do one thing. But it would take us a while to get there. OS9 launched in 1979. Just 2 years later, we get the IBM PC powered by MS-DOS, a very simple single-tasking operating system. OS9 lived largely outside the usual spotlight, despite packing all the advanced features that home users would have loved to have. Depending on your viewpoint, we wouldn't get mainstream multitasking at home until the middle of the 80s, maybe later. Even then, it wasn't as slick as Microware's Little Marvel. Alright, we've reached the end of this episode. Maybe the best way to characterize this is an exploration of time sharing through the lens of OS9. So, what have we learned here? What's the takeaway? Really, we're looking at this odd liminal period here. Time sharing was technology with pretty deep and pretty old roots. It had been developed and shaped by what was happening to larger computers. In turn, large computers were shaped by the need for time sharing. Memory management units and devices like the page box used by ITS were built for time sharing. once microcomputers start to appear, they have a lot of catching up to do. The initial attempts at time-sharing on micros had to be different than time-sharing on their larger counterparts. The hardware was just more restrictive, it was different. OS-9 is a great example of the compromises and tricks needed to bring time-sharing to the home. We've seen how this smaller version of time-sharing was different, how it adapted to the restrictive environment. It's another step on the path to our current desktop paradigm, and I think it is a fascinating step to look at. Thanks for listening to Advent of Computing. I'll be back in 2 weeks' time with another piece of computing's past. And hey, if you like the show, there are now a few ways you can support it. If you know anyone else who'd be interested in the show, then why not take a minute to share it with them? You can also rate and review on Apple Podcasts. And if you want to be a super fan, you can support the show directly through Advent of Computing merch or signing up as a patron on Patreon. Patrons get early access to episodes, polls for the direction of the show, and bonus episodes. You can find links to everything on my website, adventofcomputing.com. If you have any comments or suggestions for a future episode, then go ahead and shoot me a tweet. I'm at adventofcomp on Twitter. And as always, have a great rest of your day.